Thank you, Joel. Let me introduce our first speaker today, John Langford, Principal Researcher at Microsoft Research. So John studied physics and computer science at the California Institute of Technology, earning a double bachelor's degree in 1997, received his PhD from Carnegie Mellon University. Since then, he's worked at Yahoo, Toyota Technical Institute, and IBM's Watson Research Center. He's also the primary author of the popular machine learning weblog Hunch.net. So thank you, John.
Excellent. Okay, so there's lots of data out there. And when you take a look at the data, you notice two things. One thing is that there's a lot of data. The other is that it's odd. Now, I can only actually talk about one of these, but I decided to talk about the lots of data first because this is a big data workshop. The second one, I'll tell you briefly. When you start dealing with large amounts of data, it's usually large amounts of interaction data. That means that you need to address causality in order to learn effectively. And it turns out that there's ways to tune learning algorithms to address causality directly. And that, of course, is extremely helpful in practice. But now I'll tell you about how to just learn from lots of data directly. Okay, so when I was a student at Caltech, I was graduating, and I wanted to apply for a fellowship. So an interviewer came by, and he said, what do you want to do? I said, well, I'd like to solve AI. And he said, how? And I said, well, how about parallel learning algorithms? Right. And he said no. This is approximately exactly what he said. I mean, it was bracing. I did not get the fellowship. Not even close. And he was actually right at the time. So at the time, parallel machines were essentially used to simulate differential equations. Right? That was what parallel machines were for. They simulated differential equations for computational wind tunnels or nuclear explosions or whatever else. So I remembered that quite distinctly for quite a long time. And over time, I came to appreciate that he did have a point. And the thing which is a little bit tricky when you start looking at a lot of parallel learning which exists is, publishing is not necessarily a high bar. There's progress in many directions, right? So there's progress in algorithmic research, there's progress in parallel learning, and if the progress in the parallel is not as fast as the progress in the sequential, then it ends up not being useful. And I think we've seen that many times in the past. But I think that's changed now. I think that we have now mastered parallel learning to the extent that it composes with advances in sequential learning algorithms. And because of that, it will be a permanent part of large-scale machine learning. Okay, so this is a data set that I was playing with at Yahoo. There were 2.1 tera features in this data set. This is a ad data set. A lot of these internet companies make money by figuring out which ad you're most likely to be interested in, right? And these tend to be large data sets because there's a lot of interaction data. So when I say a feature here, what I mean is a non-zero entry in a data matrix, right? So I'm counting just the number of non-zero entries. This is a measure of the size of the data set itself. So the first thing that you might want to do is just learn a linear predictor or a logistic predictor on this data set. So stated a few other ways, there were 17 billion examples in this data set. That means there were about 125 non-zero features per individual example. There were 16 million parameters that we wanted to learn. So there were 16 million unique features. Now, 16 million was actually 2 to the 24, so there's an additional trick here, but I'll show you that briefly in a moment. And then, of course, At Yahoo, there were large Hadoop clusters available. So Hadoop is a system for doing data processing at large scale. And so it was very easy to get 1,000 cores from this cluster and use them for whatever task seemed reasonable. So now the question is, how long does it take to actually do this learning? Two terafeatures, 1,000 cores, couple days, half hour. Yeah, half hour is closer. It was about an hour. So the cool thing about this is that you can take the size of the data set and you can divide it by the time in seconds. And you get about 500 megafeatures per second. Now every individual machine in this computation had a network card which ran at 1 gigabit per second. Now, a feature is more than 2 bits. So we are exceeding the speed of light compared to single machine learning. So what you can say is, and we're essentially, this is the time, there's multiple passes of the data going on here. We're finding essentially the best logistic regression predictor. So no advances in sequential algorithms on an individual machine will ever allow finding this solution faster than we did on those machines, of course, right? Okay, so this directly addresses that guy. My trauma has been addressed. Okay, so let me tell you a little bit about how we did this. So the core thing that you need to do in order to work with a lot of machines is the core difference between a lot of machines and a single machine is communication. You have to worry about how the communication is going to work. So let's start over. When you try to use Hadoop to do machine learning, you immediately suffer. Because Hadoop was not really designed to do machine learning. Hadoop was designed to do word counts or data transformations or things like that. Things which are very easily broken apart into embarrassingly parallel computations and then combined in a relatively simple way. The core thing which goes wrong in machine learning is you need to loop over the data multiple times. So you need to have an efficient communication primitive to allow you to do this. So the efficient communication primitive that we created was allreduce. Who's familiar with MPI here? Yeah, okay. So in MPI, there's a function called allreduce. And the first thing we tried to do was use MPI allreduce because it makes sense. But MPI and Hadoop fight each other. They both think they control the cluster. And that means that just at the software level, they're not very compatible. So we just baked our own. We created our own allreduce function. And now let me show you what this allreduce function is. So suppose you have 7 nodes, and there's a number in each of these nodes, right? So 1, 2, 3, 4, 5, 6, 7. And you want to end up with the sum of all numbers in all nodes. How do you do that? So one way to do that, a simple way, which we did, was we created a binary tree. And then we add things up, going up the tree. So 1 plus 2 plus 5 is 8. 3 plus 4 plus 6 is 13. And 8 plus 13 plus 7 is 28. And then you broadcast it back down the tree. Okay? So this is not necessarily the best way, but this is a decent, simple, easy to do way. And now there's several really nice things about allreduce. So typically, you need to run allreduce on a vector, and that means you can pipeline the operation. Okay, so when you're dealing with a network, there's kind of 2 things you have to care about. One of them is the bandwidth, and the other one is the latency, and these can kind of vary independently. So when you can pipeline, you don't have to worry about latency. One of these aspects of a network just goes away. Right? So we were typically running allreduce on 2 to the 24 parameters, which on 2 to the 24 floats, which would be 64 megabytes. So the latency would just not it'd be some very tiny aspect of that computation. The other thing is the bandwidth required is just a constant factor larger than the number of bits that you're actually exchanging. So you can see that by looking at an internal node. For an internal node, you have a number coming in, a number coming in, a number going out, a number coming back, and then two numbers going out. So there's like 6 or 3 for full duplex bandwidth required. The last thing is fantastic. You don't need to rewrite your code. So that is really important. Let me try to show you. Let's see. So I'm going to show you a brief demo. This is a data set. This is a typical data set. This is RCV1. It's an older data set. But it shows you what you might end up working with. There's interesting. So something isn't quite showing up on the edge. Let me shift this. Yeah. Okay, so there's a label right here. And then there's a bunch of stemmed words. And the goal is going to be to predict from the presence or not of the stemmed words as features what the label is. Okay, so we have a bunch of labeled information, and there's actually a fair amount of it here, just on this machine. So this is, oops, let me make it readable. It's 354 megabytes, right? And now I can train on this. This doesn't quite. There, that's readable. Okay, so we're running through the data. This is a running average loss. We're doing online learning. This is a highly optimized online learning algorithm. And in a few seconds, we end up with a 4.5 or 4.6% error rate, which is about the best you can achieve on this data set by any method. Okay, so this is some code that I wrote. This is Vopal Wab. It's an open source project that I run. It's made to work on a single machine. And when I wanted to turn this code into parallel learning code, I had to add 2 lines. And that was only because I had 2 different options for how I did my online learning. It could have been just 1 line. Because you just need to look at your code and see, I synchronized that point, and that point, and that point, and then I'm done. I've continued to work on this code since this work. This work is actually relatively old. This is 2 years old, right? I've continued to improve VW. And those improvements, of course, carry over to the parallel learning itself because it's easy to maintain that aspect of things. So that I think is, in the long term, is one of the really deciding factors in the method for parallelization. Okay, so we didn't just replicate MPI reduce, because it turns out that in a Hadoop environment, you can take advantage of things. So Hadoop is great because it moves the program to the data. And when you have a lot of data, that matters. Hadoop also does, so Hadoop breaks the computation down into pieces. If one of those pieces fails, it will restart that same computation on the same data, which happens to be lying on a different node, because it replicates the data over multiple nodes. So in MPI, traditionally, if one of your nodes fails, then your computation fails. And that is a significant worry. But it turns out that you can actually get around that to some extent in a practical way. The typical failure mode that I encountered was the disk failure. The disks were a moving part in the machine, and that meant that they were the ones that ended up failing an order of magnitude more often than anything else. So what that meant was that I could run over the data on an individual machine, dropping things into a nice cached file format, and that would exercise the disk. And if the disk was going to fail, it would fail during the first pass over the data. So if it was, that meant that if it failed, it would go and restart on a disk that would actually work. And that meant that if I delayed the initialization of the all-reduced tree, I would effectively avoid entire computations failing because one node failed. So that's a big improvement. And there's one other improvement which is really important. So in order for these large clusters to be economically feasible, they have to be shared computation environments. You can't dream of having this cluster all to yourself. And because it's a shared computation environment, often the isolation between these different jobs is not as good as it should be. So that means that one of your nodes might be running much slower than the other nodes because there's 10 other processes on the same physical machine, each of which is trying to read from the disk, right? So Hadoop has a mechanism to deal with this. It's called speculative execution. The basic idea is that you take your 5% of your slowest processes and you just restart them. And then there's a race between the two processes, right? The first one to get through the end finishes. So we modified our all reduce setup routine to where it could take advantage of the speculative execution. And this was a big win. This is like an order of magnitude improvement in the time to actually finish. So at the cost of a 5 or 10% increase in the amount of computation that you do, you can decrease the time to finish by an order of magnitude. This code gets used. This is open source code. There's a dozen companies which are using VW one way or another, including the parallel learning now. Okay, so what all these optimizations mean is that you can get reliable execution out to about 10,000 node hours. Now, there probably do exist problems which merit more computation than that. But if you think about the example that I showed you at the beginning, that was only about 1,000 node hours. So we can deal with pretty large scale data just using these simple tricks. Okay, let me show you a few examples of what this looks like. So I've essentially told you how we do the communication, but I haven't told you precisely how we do the learning. And part of how we're going to do the learning is online learning, but it turns out that online learning is not the complete story. So splice site recognition is a data set where you're trying to recognize splice sites in DNA. It's one of these it's one of the few public data sets which seems to actually require a significant amount of data in order to solve effectively. If you do online learning, then you can average the parameters after each pass over the data. And if you look at the area under the precision recall curve where higher is better, you see that your performance gets better and better and better as you do multiple passes over the data. And it just keeps getting better, keeps getting better, keeps getting better. So that's nice. There's another technique which optimization people favor, which is kind of second order optimization approaches. So LBFGS is low memory BFGS. BFGS is the first initial of the last name of 4 authors who all simultaneously in 1970 discovered the same algorithm. It's a cool algorithm. It essentially, when you're doing gradient descent, which is the common way that you optimize things, you really want to go to the second term in the Taylor expansion, but you lose because the Hessian is quadratic in the number of parameters. We can't afford that if we have 16 million parameters, right? But it turns out that you can actually approximate the inverse Hessian, which is what you want to do, relatively efficiently. And then you can use that to drive things, and that gives you effective second order convergence for many data sets. Okay, so if you just run BFGS, you see that it does nothing for the first 10 passes because it only does an update once every pass. Online learning is kind of like the hyperactive squirrel, which is constantly doing something. It may not be the greatest thing, but it's always constantly doing something. And because of that, it can actually improve pretty rapidly just inside the first pass. LBFGS is kind of the slow dinosaur, which thinks really hard. Maybe dinosaur is the wrong analogy. The slow philosopher who thinks really hard and then makes a step, and then makes a step, and then makes a step, right? Slow professor? That would be a fun one. Anyways, LBFGS has a problem with starting. However, it ends up doing pretty well in the long run. And now you can just do online for one pass and then just do LBFGS. And that works really well. So that's fantastic. You get the benefits of both. Yeah. Oh, I know, we could do students and professors, right? So you have the really eager students who don't know what they're doing, but they're still trying to do something. And then you have the professors who think really hard, and you get the benefits of both. Okay, there's other approaches people have proposed for parallelizing things. And there's many different kinds of, is more than just this. These are the ones which are most similar to what I did. So there are approaches which are meant to parallelize large-scale learning, meaning when you have a lot of data and you just want to learn maybe just a simple logistic regression algorithm. So the blue line is an approach where you create an overcomplete partition. So every example exists on 1/4 of the machines, right? So you take your initial data and you create an overcomplete partition, so every example is replicated maybe 25 times on 100 machines. And then you run online learning once over that, and then you just average things together at the end. The red line is mini batch. So the idea with mini batch is that you instead of waiting until the end to average things together, you just try to average things together very quickly, right? So so you have a bunch of different machines, each of which has the model. You compute a gradient, and then you average together the gradients, and then you take a step in the direction of negative gradient. Okay, so it turns out that our approach works better. It turns out that the contribution of the professor is indeed important, essentially. And the truth is actually worse than this graph would make you believe. Because this was 40,000 node hours right here. This was a very difficult computation to do. If we tried this computation, there was a good chance it would fail. This was substantially more than ours, and this was this is ours. Okay, so since this paper came out about 2 years ago, there have been other approaches to online learning people have discussed. I think the one which kind of makes people most enthusiastic but makes me most cautious is asynchronous approaches. I think there's times when you have to do asynchronous learning. So what we mean by asynchronous learning is essentially when you run your learning algorithm, you don't get the same result twice. That's what it means in practice. So one of the drawbacks of all reduce right here is that it's a barrier. So you have to wait for the slowest node. That's why speculative execution was so helpful for us, right? But even with speculative execution, we're still paying perhaps a factor of 2 or 3 for having a synchronous computation here, right? So people have been experimenting with approaches which remove a barrier. And I guess my general belief is that if you want to have these kinds of algorithms, then you should make it so that they can run synchronously whenever you want to debug them. Because trying to debug an asynchronous algorithm is kind of cruel and unusual punishment. Okay, thank you. Yeah, questions? Yeah.
John, on your last bullet, you repeat computation unnecessarily and actually cause the network to be even more loaded.
No, actually, so the network doesn't get used much when you're doing speculative execution. Yeah, so the cluster doesn't get that overloaded. It's only 5 or 10% extra computation, right? So it's only in the first pass that we have to do this, or that we do this, and yeah, it's not a problem in practice. I think the benefits far outweigh the cost in this case. Yeah?
I was wondering if, people in the sciences, if they wanted to use a tool like this to speed up their computation, what is a good starting point?
I mean, the tool is open source. The tool, look up Vopalwabbit, VOWPALWABBIT. This is an open source tool which is used by a dozen companies, like Amazon, Facebook, Yahoo, Microsoft, IBM even, for many different applications, right? And all the code is in there, so that's where I would start.
Yeah, I was wondering for non-technical people.
So you don't have to know the guts of the code in order to use machine learning algorithms. Generally, the level of knowledge that you need is substantially lower. You have to understand what supervised learning is and how to show that you've made good progress in machine learning. But I think that's the kind of thing which you can pick up in a day. There's a class I taught at NYU which is videotaped, and you could go and look at it. But maybe that's not the right one. So that's a more advanced class. Andrew Ng has a great big MOOC that he ran with an introduction to machine learning. And you just sit through a few lectures and you'll see how to understand basic supervised learning. One more question? Yeah.
So say there's millions of features. You treat each word as a feature or word count as a feature.
Oh yeah, actually, so for the big data set, what you're really looking at is vocabulary cross vocabulary. Because you're looking at kind of search across advertisement contents, right? And that's why you get a relatively large number of features. You also often throw in things like the advertiser ID, and there can be a lot of advertiser IDs.
Okay, thank you, John.
Yeah.